In the heart of 17th century Europe, two of the greatest minds in the history of science were working completely independently on something revolutionary, something that would forever change physics, mathematics, and the very way we describe the world: calculus. But who was the real inventor? Isaac Newton or Gottfried Leibniz? Welcome to the most famous rivalry in the history of mathematics. When you hear the name Isaac Newton, what comes to mind? An apple falling from a tree? Gravity? The laws of motion? Fair enough. But what if I told you Newton also invented calculus and kept it secret? It's the summer of 1665. One of the deadliest epidemics in England's history is sweeping through London and the surrounding towns: the Great Plague. Over 100,000 people will die. Panic spreads. Families lock themselves inside their homes. Doctors, helpless, wear eerie bird-like masks stuffed with herbs. Even the University of Cambridge shuts down. Students are sent away. Among them is a 23-year-old young man, Isaac Newton. He leaves the city and retreats to his childhood home in Woolsthorpe, a tiny village lost in the English countryside. There, far from everyone and everything, surrounded by silence and uncertainty, something extraordinary happens. In what he would later call his miraculous year, Newton begins laying the foundations for the law of universal gravitation, modern optics, and something else we now call calculus. To him, it was the method of fluxions, a way to describe continuous change, as if quantities were flowing through time like a liquid. Fluxions represented the rate at which a quantity changes, what we now simply call derivatives. Let's imagine we have a body moving along a straight line. We fix an origin in our reference system, and suppose we know the position of the body as a function of time, for example, through the following equation of motion. Thanks to this expression, we can determine the exact position of the body at any moment in time. For instance, at the initial instant, when our t equals 0, the body will be at the origin. After 1 second, its position will be, and so on for other time values. Now, let's say the body moves for 30 seconds. What is its average velocity during this time? The average velocity is simply the distance traveled divided by the time taken. But what if we want to know the velocity of the body exactly at t equals 10 seconds? One approach is to calculate the average velocity over a very small time interval around t equals 10. For example, between t equals 10 and t equals 10 plus h. However, this still gives us only an approximation because it's based on a finite interval. To get the instantaneous velocity at t equals 10, we need to let h approach 0. In other words, the instantaneous velocity is the derivative of the position with respect to time. And here's the surprising part. Not only can we calculate the exact velocity of the body at a specific moment, like t equals 10, we can actually determine the entire function that describes how the velocity changes over time. By knowing the position at every instant, we can deduce the velocity at every instant. And all of this is made possible by one of the core tools of calculus, the derivative. Newton's insight was incredibly deep, but he didn't publish it. He wrote treatises, filled notebooks, sent letters to colleagues, yet everything stayed hidden in his drawer. It wasn't until 20 years later, in the Principia Mathematica, published in 1687, that he hinted at these ideas. But even then, he disguised them in classical geometry to make them more acceptable. Newton was protective of his discoveries, maybe even obsessed with control. To him, calculus wasn't a new theory to be shared. It was a powerful tool, a way to understand the cosmos. And while Newton, isolated from the world, was developing his secret method, another man in another country was reaching similar conclusions, but in a completely different way. His name? Gottfried Leibniz. Philosopher, mathematician, jurist, linguist, engineer. Leibniz was a true universal genius. He traveled across European courts, debated with kings, and corresponded with scientists all over the continent. He dreamed of building a logical system that could contain all human knowledge. Between 1675 and 1676, without knowing anything about Newton's work, Leibniz developed his own method for studying change in the areas under curves. He called it calculus. His real revolution? Notation. In a diary entry dated November 1675, a symbol appears for the very first time, a symbol that would go down in history. The integral sign, inspired by the letter S for summa, meaning sum. He realized that dividing the continuous into infinitely small pieces was the key to calculating areas, speeds, slopes, symbols we still use today. Let's imagine we have a quantity, called y, that depends on another quantity, x, through a rule or function we'll call f. We plot this function on a Cartesian graph and ask ourselves, what is the area under the curve, between the curve and the x-axis in a certain interval, for example, from x equals a to x equals b? If the function were constant, the answer would be simple, base times height. But what happens when f is not constant? A natural first step is to break the area into several thin vertical rectangles. Each rectangle has a width called delta x and a height equal to the value of the function at the left end of the rectangle. In this way, we're approximating the area by summing up many small rectangles. The thinner the rectangles, the more accurate our approximation becomes. But the real breakthrough comes when we let delta x shrink to 0, meaning we take infinitely many rectangles, each with an infinitesimally small width. At that point, the sum becomes something much more powerful, a definite integral. The integral symbol stands for a continuous sum. We are adding up infinitely many tiny contributions, each of the form f of x times dx. Each term represents a tiny piece of area, the height f of x, multiplied by an infinitesimal width, dx. Newton had his fluxions, marked with a dot over each variable, but they were hard to manipulate and far from intuitive. Leibniz's notation, on the other hand, was modern, modular, elegant. It wasn't just a discovery, it was a language. And unlike Newton, Leibniz published. In 1684, one of his articles appeared in the Acta Eruditorum, a scientific journal in Germany. For many, this marks the official birth of calculus. Within just a few years, mathematicians across the continent were adopting Leibniz's notation. Calculus spread through Germany, France, Italy. Newton may have discovered the foundations of calculus first, but he kept them to himself. Leibniz came a few years later and opened the door to the scientific world. But then, something happened. When English mathematicians began reading Leibniz's work, they noticed striking similarities. How could a foreigner understand concepts so close to those Newton had developed decades earlier? The spark ignited in 1699 when, for the first time, an accusation emerged. Leibniz copied Newton. Newton, who had avoided open conflict until then, began moving from the shadows. By 1703, he was president of the Royal Society, the most prestigious scientific institution in England, a position that gave him authority, influence, and control over the British academic world. To clarify the matter, the Royal Society formed a committee to investigate who had truly invented calculus. An official inquiry. But here's the absurd part. The final report, the one that accused Leibniz of plagiarism and praised Newton as the sole true inventor, was largely written by Newton himself. And worse still, Leibniz was never informed. He had no chance to respond or defend himself. In essence, Newton was judge, jury, and witness in favor of his own case. The verdict was crushing. Leibniz, the imposter. Newton, the rightful genius. In England, only Newton's method of fluxions was taught, but on the continent, it was Leibniz's elegant notation that triumphed. This split would isolate British mathematics for nearly a century. November 14th, 1716. Gottfried Wilhelm Leibniz dies in Hanover at the age of 70. He is alone, bitter, no official tribute, no members of the court present, only his secretary, and a nearly anonymous grave. And yet, Leibniz had been one of Europe's most brilliant minds, but the dispute with Newton had tarnished his name, at least in the English academic world. 10 years later, in 1727, Isaac Newton also dies, but the contrast couldn't be greater. Newton receives a state funeral. He's buried with full honors in Westminster Abbey, among kings and poets. His name is already legend, the genius who decoded the universe. Two men, two extraordinary minds, two different ways of thinking, but one single monumental discovery: calculus. And so, after this journey, we still wonder, who really invented calculus? Newton, who discovered it first, but kept it hidden for years? Or Leibniz, who published it, shared it, and turned it into a universal language? Maybe the answer isn't in the names, but in the legacy. Calculus was born twice, in two different places, with two different approaches, but it survived time, pride, and rivalry. And if there's one lesson this story leaves us, it's that disputes fade, but ideas endure. And now, it's your turn. After everything we've seen, whose side are you on? Team Newton? Team Leibniz? Or do you believe calculus is too great to belong to just one name? Tell us in the comments, and don't forget to subscribe for more stories from the world of math and science.